Step 5.3, model-based clustering. Now we want to look at finite mixtures of regressions, where we have we want to cluster data. We have a dependent variable and explanatory variables, and we assume that the regression coefficients differ between the groups we are interested in. And to illustrate that, we use an artificial data set which is available in package MSA. So we're loading that artificial data set theme park, and that contains two variables, pay and rights, which represent how much our respondents are willing to pay depending on the number of rights available in a theme park. So we are plotting pay as on the y-axis versus rights on the x-axis, and using that data set here, that's the label for the x-axis, label for the y-axis. So that's what the data set looks like. Zoom in. We see we have here a group of respondents where approximately any additional right we have gives a certain gives a fixed additional willingness to pay. Whereas here we have a second group where we see that if there are too few rights, they're not willing to pay much at all, and if there are already a substantial amount of rights available, any additional increases the willingness to pay more. So we want to fit now a model which allows us to detect these two groups in our data set. And one might then want to target those differently. So how do we do this? We're setting a random seed, because the EM algorithm is depends on the initialization, which is random. And we're using function step flexmix from the package flexmix, and we want to have a regression model. So dependent variable is pay versus rights. And we think that it's not a linear relationship, but potentially there are also higher order terms. So we think because the additional value depends on how many we already have, so the marginal effect changes, we model this using a squared term for rights. And in R, we can say rights to the power of 2, and we need to protect it to say we literally mean this should be right squared and not a main effect plus an interaction effect of that variable. We want to evaluate that formula using the theme park, and this means in a regression model we would be modeling pay as dependent variable. We have an intercept, which is by default always included if we don't exclude it. We have a coefficient for the variable rights, and we have a coefficient for the variable rights squared. So there'll be 3 regression coefficients, and we're fitting 2 groups, k equals 2, and we want to repeat that using 10 random initializations. We repeat the MM algorithm. We don't want to have progress information plotted, and this is what the result is. This is the best model among the 10 random initializations for 2 components, and we see if we then classify respondents to groups, we'll get one group with about 120 observations, the other about 200 observations, and the M algorithm converged within 20 iterations. So let's look how does the clustering did work. We can plot the same scatter plot as before, pay versus rights, but now we use different clustering depending on to which cluster our observations were assigned. So we use our fitted model and we use clusters on it, so that will return the vector of 1s and 2s where each of the respondents are assigned to. So this will give us now the scatter plot with colors, and what we want to add to that scatter plot now are also the curves we originally drew the data from. So that's because it's artificial data, we know what is the true functional relationship. So for segment 1, this one here, it's just a straight line, so y equals x plus an error, and for segment 2 we have y equals the proportion 0.0125 times right squared. So these are the 2 functions which are true underlying functional relationship between the variables in the artificial data, and then we can add those 2 functions using function curve, where we put in the function definition, which is a function of x, and then we say for which values of x do we want to evaluate the function. So we say from 0 to 50. So that function is plotted from 0 to 50, and curve could either open up a new plotting window and plot the curve, but add equals true means we're reusing the same plotting window and we are adding just a line to it. And we see we were able to find those two groups which differ in how their willingness to pay depends on the number of rides. We can look at the fitted regression coefficients for the two groups using function parameters. So we see for component 1, which is the black one, we have an intercept value of 1.6, which should be 0. We have a coefficient of rides minus 0.12, and here it's the coefficient for the squared value, which should be 0.0125. And with the data generating process where we created the artificial data from had a standard sigma value of 2 for both components, and here it should be 0.10. If we want to get reliability estimates, so how well are we able to estimate each of the coefficients, and did we see that, for example, for component 2 this is not significant, we can refit the model because originally the model is fitting using the M algorithm, but the M algorithm doesn't give us estimates of the standard errors. We need to refit it using a different algorithm, which gives us access to the standard errors, and the summary function will then return that output, telling us that for component 2, this is our estimates, original estimates we had here before. These are the standard errors, set values, and the p-values associated with it. This would indicate for component 2 that neither the intercept nor the coefficient for right squared are significant, and we only have this linear relationship, and we see here that's very close to 1. So we were able to identify this. Here we also see that this coefficient has a p-value which is very small. The others would also be significant at the 5% level, but this could also be due to the case that we are restricting this to be positive.